Okay, well, in that case, let's go ahead and get started. So I'm Frederick Kautz. So unfortunately, my counterpart, Ivan, was not able to make it today, so it's just going to be me. But he did help me put together this deck, and we spent quite a bit of time trying to work out what it is that we want to show all of you. So in general, what I'm going to try to do is I'm going to try to describe move it forward. So I'm going to try to set like what is a container. So I don't want to make any assumptions that people have a full understanding of what a container is. And what I want to do is talk about a container from a networking perspective. What's out there, what's available, what can you potentially use now, what's coming through the pipeworks. I want to describe as to like why does everything not just work now? Like we have all this stuff with virtual machines, and why can't we just go off and reuse a lot of that work? Why are we as a community re-engineering a lot of the tooling and APIs that exist? And we'll also cover some of the deployment models that we've seen as well, and we'll cover some of the technologies. So in terms of like what is a container, or what is it that we're going to try to focus on? So first, what is containers? We're going to focus on container technology, container management and orchestration, and container networking. So moving on. So exactly what is a container? So a lot of people like to think of containers as sort of like a virtual machine. Like you stick this process into this box, this container, and then it runs, and you can start it like a VM, you can stop it like a VM, and conceptually it helps a lot to get in. But when you start looking at the differences, it turns out there's a lot of interesting differences between them that are quite subtle. So when we talk about a container, it's not moving. Let me try resetting it. Oh, weird. Okay, worst case scenario, I'll pull it out and put it in again. So let's see if I take it off full screen. Okay, I think I know what I'm going to do. I'm going to move this here. And see if I hit present, does it do the same thing? Okay, so the only problem is I can't see it. Give me a quick moment and I'll fix this up real quick. Is it okay if I use one of the microphones instead? Okay, my apologies. So anyways, going back to where we are, let me go ahead and hit present. Okay, so when we talk about what a container is, so a container in a broad sense covers both containers as what we commonly hear. It also covers VMs, covers even a process itself can be considered a container. But when we talk about containers, we typically talk about specifically process containers. So think of a process container as an environment that has been set up by the operating system in order to isolate a process. So it gets its own file system, it gets its own network stack, it's its own process file tree, and so the kernel does extra bookkeeping in order to make sure that it all works. So this is quite very different from a VM, where a VM will literally emulate an entire system and hardware and NIC cards and so on. So, okay. So how does this end up working? So there's a few technologies. This is not exclusive. This is not like totally inclusive, but in general, the early most important parts are C groups, which allow you to monitor your resources, allow you to limit your resources. A lot of this work around C groups, if my memory is correct, was contributed by Google, and Google used them internally for several years, and the rest of the community, like C groups was available, but it didn't really catch on because of some of the difficulty. The next one is the mounted file system. So what ends up happening is every time you run a container, literally a new mount will be created in a file system tree, and it's sort of like an advanced CH root. And so the CH root ends up, the process is then rooted to that particular CH root, and in ideal circumstances, you can't escape. There are exceptions to that, like if you run it in a privileged mode, or if someone were to find a bug in the kernel and exploit it, then yes, they could potentially escape. But in general, processes are isolated to that subdirectory on the host. So each one gets their own network namespace, which is really important for us because that allows us to do really interesting workflows beyond what the host provides. So it means it gets its own IP address, gets its own DNS. When you open up a file descriptor, that file descriptor is bound to that particular namespace. Whenever you run IP tables, turns out even IP tables is also namespaced. So if you have enough privileges, and usually you don't, but if you have enough privileges, you can actually run IP tables that's bound to that namespace. And so a really good talk, if you want to see into the details, a lot of this is Jaume Devesa created Anatomy of a Container Namespace, C groups, and some file system magics. And he gave a really great talk on this. I recommend you look it up if you want to get into like the really nitty-gritty details. So what's interesting with a network namespace is you literally get a full network stack. So you get your own network interfaces. It traverses over its own. You can hook them up to bridges properly, create novel workflows. And so usually there's two, in most SDNs you see two forms of connectors. So the first one is veth pairs, which is the most common one, and the second one is using the ton tap, which the difference between the both of them is the veth pairs are the data path in order to manage and to work with them is non-blocking, while IOCDL has some performance issues. So in general, if you have a choice, if you're want to jump into some of this, I highly recommend you look at veth pairs rather than looking at the ton tap. And so typically what ends up happening, like early Docker, if you looked at the networking structure of it, the early structure was you set up a Linux bridge and you then hook up veth pairs. One side of the pair would go to the bridge, the other side of the pair would go to the container inside of the new network namespace. So real simple. So what we're in more advanced use cases. So if you look at the code in Flannel as an example, one pair goes to the container, and then the other pair exists on the within the host. But what ends up happening, I don't know if it's a host or if there's another container that it brings up with that inside. But what ends up happening is that second veth pair is then read using standard socket I/O. You can do read, you can write to it, and so it'll read the data off of that, and it will transform that into UDP or into VXLAN or wherever it needs to go. And in general, a large number of SDNs work in that exact same way. So OVS is a little bit more interesting in that they have their own style of bridge. So they have a patch, but in general, Yeah, with OVS, what you want to do with OVS is there's a set of commands you can run that'll create an interface, and that interface will then back into the OVS bridge, and then that OVS, and then you can then move that that interface into the container's network namespace. So the company that bought SocketPlane was Docker, and so a lot of the libnetwork stuff that you see or so on was like was done through the SocketPlane acquisition. So they basically bought a team that has a lot of this experience. So and they're a pretty solid team. So, but yeah, in general, yeah, you're correct with that. So that interface will go into OVS, and then you can manage that through OpenDaylight or whatever SDN controller you want to use that works with it. Yeah, and feel free to ask questions. Like I think people get more interested as well when there's questions asked. So the idea behind it is we wanted to. So this was a little bit more of an overview in terms of the Docker side. So a little bit of background on my part. So I was involved with Docker really early on as a community contributor, and part of the use case, if you look at where Docker originally came from, it originally came from a platform as a service environment. So you look at Docker coming from the Doc Cloud environment, their lessons learned were from creating a platform as a service. So things that they learned, like you look at the initial use cases, you have the ability to hook onto to directly reuse the host. So in other words, don't even create a network namespace, just use the default namespace. But more generally, what you have is the bridge with veth pairs. But the problems that we ran into it is the Linux bridge, you have to have a way to NAT in and NAT out, and so that actually becomes problematic. Like I don't know if anyone's tried to run something like Hadoop HDFS or Erlang OTP on in early Docker. You could run it on a single system, but you try to run it outside of that, it was a complete nightmare. And so a lot of the newer technologies that we have like help us run these distributed systems. So, see, this is stuff that I've mostly covered. Okay, well, so continuing on. So when you create a packet, you're still going through the Linux TCP IP stack, and this is actually quite important. So it turns out that there's some performance. I don't want to call them issues, but there's certain performance considerations that you have to consider when you use the Linux TCP IP stack. So when you create a veth pair, it's not like a normal socket that all the data is just going into say OpenDaylight's OVS or so on. It actually creates a full packet, creates what they call an SK buff. That SK buff goes through an entire pipeline which runs IP tables, runs various hooks and so on. And so this becomes it has a performance impact. So you have to take that into consideration. And however, the overall model is relatively simple. So you don't have to worry, am I creating this TCP packet properly? You don't have to worry as much on, like if you set the firewall parameters correct, then you have good confidence that it's going to probably work right. So some prominent examples. Let's see. We've already covered OpenDaylight. We see this model also used in OVN. So OVN is Open vSwitch's internal implementation to expand out OVS. So Flannel and UDP has a UDP and VXLAN mode. They also use this veth pair path. And the initial implementation of VPP also used the veth pair. There's actually something, I was having a talk with Ed earlier today though, and with Keith Burns, and they were mentioning that they have a memory mode which fully bypasses the kernel. So what ends up happening is they carved out a section of VPP, and then they would overwrite socket, and with the VPP shared memory driver, and then from there, then they get very fast very fast reads and writes between containers. So as opposed to you run it through your first veth pair, you create the packet, and then you run it to the second veth pair, and then you recreate the packet yet again. So you end up avoiding that entire path. So just it's something new that's coming up. Okay, so so in general, you can just describe most of your interfaces or most of your SDNs that are in the container space into three main areas. You can describe them as layer 2 or layer 3. So with the layer 3 interface, what the typical scenario is you just create a private overlay standard as to what you think of when you think of Open vSwitch or OpenDaylight or so on, or if you're working in a neutron world, you get the same semantics. But so in terms of layer 3, let's see. So OpenDaylight is layer 2. Layer 3 is particularly interesting in that instead of creating a new overlay, what you do in the layer 3 is you end up doing a really clever hack with the routing tables. And so what you do is you have an IP address for a container, and that IP address is given a route on all the other hosts, and that route is inserted into every routing table. So you end up creating this private network where the knowledge exists not in a traditional SDN. The knowledge exists within the routing tables, and you have to have some mechanism to manipulate all the routing tables. And the two common ways to do this is usually through a BGP, and the second way is that we're starting to see is the use of etcd from CoreOS to manage the distributed state. For those of you who haven't used etcd, you can think of a system such as Zookeeper. Think of it like a version that was created more for containers. So in general, when a packet is sent, what happens is that packet traverses through that packet ends up traversing through the veth pair, and then once it reaches the other side, it hits the bridge, and then that bridge, when it gets routed out through the Linux routing system, then it'll do the lookup there and send it off to the correct place. And so it's a very simple model. The things you have to be careful with, though, you very likely usually need some type of an on-ramp or off-ramp in order to convert from your pseudo overlay into your network. And interestingly, you don't even. The other thing you have to be a bit careful with is, depending on how you set up your BGP, you want to make sure that your BGP is set up in such a way that if you have other BGP packets on the same network, that they don't interfere with each other. And there's standard ways, like if you have an expert with BGP, or you go with a standard vendor, they're usually pretty good at setting that up. It's just something that you have to just be aware of. And the good news with it is that with this layer 3 approach, you don't have to know anything about the underlying network. So you could use pretty much any network, and it'll typically work. So the main examples that I've worked with are primarily Calico and Contiv. Calico was created by originally the Metaswitch people. They've actually spun off into their own company, which I think was called Tigera. Contiv is a Cisco-driven effort. So, and both of these examples use the BGP approach. So, some of the problems that we're running into. Let's see. I feel like I skipped over a slide because I had a layer 2 section. No, I'll talk about layer 2. Okay, so one of the things with when you start looking at layer 2, I'll ignore the slides for a little while. So So what ends up happening on the layer 2 side is we have problems with how we want to, with how you manage. Like you have multiple APIs that came out from the container world. So you have libnetwork, you have CNI. So libnetwork is primarily used in the Docker world. CNI is used primarily if you want to run Kubernetes, then you'll use CNI. And so from the So what you need then is a way to translate into whatever your SDN system is. So there's a couple of ways to do this. In the OpenDaylight world, one particular option is you can use Kuryr. So Kuryr is basically a neutron-based basically converts from CNI or libnetwork and converts over to neutron, and then it just works from there. So we were able to successfully run libnetwork, and the Kuryr team is also very busy in trying to get the Kubernetes workflow to be stabilized. So they showed a demo of Kuryr back in the OpenStack summit back in Austin. Then they showed off a demo showing the system working, but there's still a lot of considerations that need to be done. So anyways, some of the existing problems that we have is, as well as many of the techniques that we use in VMs don't necessarily translate to containers very well. So that's why when you look at the various VM APIs, like even looking at something like Neutron. So Neutron has a problem where if you want to run containers bare metal, then that's relatively easy because you can basically create an interface, pass it into OVS, and it just works. What happens if you want to run where you're running a container-based API like libnetwork or CNI, and then that's creating UDP or VXLAN, and then that ends up being ran on top of Neutron, which also maybe uses VXLAN. So you end up with this double encapsulation, and this double encapsulation is very problematic because what happens is your packets, they become difficult to inspect, they become difficult to run your quality of service on. You end up with a significant performance hit. The numbers that I've heard from some, I don't have them with me to show off, but I've heard maybe up to around 40% degradation in terms of overall performance. So if you're in a telco space and you're trying to get a huge amount of throughput through, I mean, 40% being trimmed off just because you decide to use a container is huge. So those are the types of problems that we need to solve for. And interestingly, the layer 3 approach doesn't run into the double encapsulation problem, but then you still have the on-ramp, off-ramp that problem that needs to be solved. And so right now they're using on-ramp nodes, as I mentioned before. I don't know if there's any that can do where every host can do an on-ramp or off-ramp. Yeah, that's correct. So, but you don't have the double encapsulation problems. So you. Yeah, so your performance is still. Yeah, and interesting. I've also heard the OVS team. They've gotten some patches recently that performs a lot of the ACLs and within OVS itself. And those ACLs, they were telling me, have a significant performance increase over using IP tables. And not to mention, if you're using Open vSwitch, then you also gain the ability to drop in something like DPDK and so on. And you don't get that ability if you go with the layer 3 approach necessarily. Sure.
What is the distinction you made between container SDN and the infrastructure SDN, and why it couldn't be the same?
Oh, yeah, well, that's what we're trying to do. So the distinction is, suppose you run Kubernetes, right? And so you might have Kubernetes, which then runs Flannel. As one example. Flannel will then, let's say you go with a default installation, you'll have like a UDP connection in between. And so what ends up happening is if you decide to run like within VMs, then you have Flannel running UDP and then UDP on top of like VXLAN.
Okay, so you're not addressing that presentation, how you can actually replace the container SDN with the infrastructure SDN with a single one.
Yeah, and that's what the purpose of Kuryr is to lift up the overlay that's provided by Neutron, and then perform that last mile hookup into the container, so that way then you're no longer running the SDN, you're no longer running flannel or...
That's not the existing, right? You're not, eventually the target where we want to go.
Yeah, it does exist to some degree at this point. So the lib network support exists at the moment. There's basic Kubernetes support for it, but there's a lot of work that needs to be done in this. Like if you want to have a really high impact area to contribute in this space, this is one of the problems to solve. So. Yeah, and not to mention that when you're working in neutron world, then you also have you also want to be able to do load balance as a service or firewall as a service and so on. So if you just run the normal container APIs, like you don't gain seamless access to this. Like the integration is painful. So. Let's see, do I want to talk about the data paths? We'll go and skip the eBPF part. So other problems that we're running into as well is right now the standards are still developing. So we're finally getting OCI standards scoped out. We're finally getting the most important ones on the container specs, at least from the areas that I've seen, is so more important than Docker or Kubernetes or so on, in my opinion, is getting that spec right. Because if we get that spec right, then we enable the entire industry to progress forward. And so the first one that's gained a lot of traction was the runC spec. And so Docker carved out a section of their code, contributed it into the Linux, I believe, to the Linux Foundation, and that's now the runC spec. And second part that's been developed, this part hasn't been carved out, but rather has been developed independently through Docker, Red Hat, CoreOS, Google, and so on, all collaborating. Several other companies as well, apologize for not mentioning all of them, is the image format. And so this image format has a couple of things. So first it has the tarball, which is your file system, and then it also has an entry point, and it has a list of, there's a manifest that shows parents and which layers belong to a particular image. And so we finally getting to a point where we have that very close to being standardized. And so so we're getting very close, but at the same time, a lot of the networking, like I don't recall there being any major effort yet to standardize, like this is what the container networking spec should look like, because we have two competing efforts. We have with the lib network and the CNI group, and very, very different targets in terms of like where they want to take it. So realistically, what will probably end up happening is both of them will probably continue to exist independently. And which means that as an SDN provider, then you have to either have a way to, if you want to support containers, then you have to have a way to work with both of them ultimately. So there's also a lot of work that's been going on in the Neutron API. So the double encapsulation problem that we were mentioning before, the way that the Neutron team is working to solve that is there's a new set of patches that are going in which talk about VLAN trunking. So VLAN, you VLAN tag your packets, and then you then trunk the host, and then that allows you to run a container in the VM and be able to discriminate between like which packet goes where. So that's so that was spec'd out. I don't know what the status is on the implementation of it at this particular point, but there's a lot of work that's been focused on that. Like for past several months, people have been working on those specs. And the big question is, are we going to see community adoption? There might be another way to do it that turns out to be a better way or so on. I don't know if that'll happen or not. But in general, like the Neutron APIs need to be implemented and they need to be adopted. And if you don't get the actual APIs implemented in the VLAN trunking area, then of course as a container you can't make use of it. So anyway, talking about, let's go and move on towards heterogeneous environments as well. So when you say let's go mix in VMs and containers. So first we mentioned about container SDNs being separate from VMs. So part of it is like how do we end up mixing these technologies together? What happens if you talk about mixing something like Windows and Linux within the container environment as well? So remember that there's now a native version of Docker Windows, and are those going to support VXLAN? Are they going to support some other encapsulation method? And so right now, like if you run Kuryr runs only in Linux. So there's no, as of now, there's no Windows support that's been added in. And the container scheduler. So if you look at something like Kubernetes, these are primarily designed to focus around what we call a 12-factor app, which holds very little state, holds very little information, and gives you the ability to horizontally scale out and so on. So there's issues with how do you scale, and one of the things with it is that you need to have the ability to your scheduler has to have some knowledge as to how to handle resources such as networking, and many of those hooks and APIs don't exist yet. So thanks. So there's a lot of work around the tooling around this area. So I'm pretty sure if your approach, like there's a Kubernetes network SIG, so that if you want to get involved in some of these discussions, highly recommend that you show up to them. Specifically Kubernetes network SIG. If you put that into Google, it'll pop up. So I think I've already covered a lot of stuff. So we already know about like the bare metal. We've talked about the container container on bare metal managed by OpenStack, which worked out of the box about a year ago or so. And that was work done primarily through the Ironic, Magnum, and Kuryr efforts. There's a couple new models that are starting to come out as well. So one of them is a VM container, such as Clear Container and Hyper. And so what a Clear Container is it's sort of like a hybrid between a VM and a container, where you run it as a VM, but certain sections of the operating system's core memory is shared, but you end up with different resources being parsed out in terms of memory and so on. So this particular hybrid, it would allow you to run technologies that are developed for your VM, but simultaneously give you many of the benefits of the container in terms of the deployment models, But one of the problems that we have with this is that your host has to know how to deal with this, and I don't think that's hit any the Linux kernel mainline. So I believe Intel has an effort on that. So they have a specific effort to run Clear Containers, and they have a VM that you can download and try it out with. And the container and VM model that we spoke about. So I think we covered all this stuff. Okay, so let's jump into some of the NFV use cases. So one thing that many NFV vendors are starting to do is many of them are starting to consider working on moving their NFVs over to a container. So the main benefit is the density, since you're not using as much memory, spinning up a bunch of operating system, and you can spin up a container incredibly fast. But the problems that we run into is that when you start looking at how do you manage these particular systems, like is Kubernetes the right model for it? Like, if you have to maintain state over time, then you may end up running with some problems with that. And some of the applications may actually require rewriting. So one in particular thing, you can separate your efforts into, I guess you would say, two major areas. Like you have the control plane and the data plane. So you can think of it as like you can have like a data system for containers where the actual NFVs that are running, but then you can also containerize like the NFV manager itself. And so if your NFV manager goes down, then your orchestrator, your Kubernetes orchestrator could then notice that it's down or notice that it stopped working through its C group metrics and so on, and then spin another one up on maybe on a different system if that system's having problems. But it doesn't solve problems related towards the actual NFV manager itself, because if it has state that needs to be maintained, then that state has to be stored somewhere so that even if this process goes down, you can either rebuild your state or you end up having somewhere you can pick up your state and just continue moving on. So putting it into a container does not necessarily mean that your application is going to suddenly turn into, or is going to become robust. So you have to actually consider the actual application itself. And in a container, if you're using something like SRIOV or DPDK, that becomes a little bit problematic. So there's a couple of problems that we run into. So first, when you run, say you want to run SRIOV, then so you'll have certain modules or certain resources that are available on the host, and you have to then expose those to the containers. And there's a couple of ways that you can expose that out. So one of the ways you can do that is through bind mounting the individual systems in the file system, and simultaneously giving the system enough privileged access in order to call the API, the kernel APIs that are necessary to run. But then you also lose some of the security benefits as well, because you're not running in a privileged mode. The DPDK one approach, of course, you lose you end up not being able to see what sharing the NIC between containers, so you end up reducing your sandbox isolation if you go with the DPDK approach. And in general, what you end up having to do is you end up having to establish a DPDK application, and then set your kernel up, and then start the container up, and it becomes very, you end up having to do a lot of management outside of the container itself. So that's a significant problem that we have at this particular point. So we covered this. So anyways, yeah, I want to leave it open for some questions. So, is there any particular topic that people want to discuss or ask questions on? Anyone want me to move a slide back so that you can take a picture?
Let's take the last thing.
Sure. Yeah, like this is what I was talking about in terms of like your VNF manager state. Like your VNF manager has to be designed to fail gracefully. It has to be designed to scale out potentially horizontally depending on your system's need. If you want to make use of full use of Kubernetes, of course you can run a single container, and if your pod goes down to zero instances, and then it'll spin another one up. But yeah, it doesn't solve application-related problems. So, sure.
So that's how you're talking about using DPDK and basically breaking up a whole NIC and handing it to a container.
Right.
I'm not very familiar with the VET interfaces yet, but is it possible to type a VET device from like the DPDK container into like a consuming container on the same host?
So there's a couple ways to do that, but you probably don't want to hook a VET directly up to DPDK. So I'll give a really brief overview of DPDK for people who are not familiar with it. So you can think of DPDK as a set of libraries that are designed to interact directly with the NIC hardware. So think of it like direct memory access, like you have from a hard drive to memory, when the kernel can say load this from here to here. So you can think of it like direct NIC access for where your application can literally write its own TCP packets and send them off to the NIC, and then the NIC will then write them off to the wire. And so in terms of hooking up a VEF, that doesn't make as much sense because now you're introducing the kernel.
To routing through the VDK interface.
Right.
From sourcing from that.
Yeah, and that's, so what ends up happening, so there's a couple efforts that I've seen. So if you look at OVS and VPP, both of them are working on sticking DPDK in there. So what you could do is you can hook your interface, whether it's VEF or through some other means, hook it so that once it hits the OVS bridge, then OVS would then write using DPDK. And this is actually a much better approach, in my opinion, than just generally than just giving a container a DPDK interface. There's some exceptions of that. I mean, if you need absolute performance, you only need one, then sure, like go ahead and take that model. But if you want to gain full DPDK acceleration for all of your containers that are running the SDN, then yeah, it makes sense to do that. So make OVS own that DPDK instance, and then drive everything through OVS and gain that acceleration.
If you're, I mean, just a comment, we actually have on the Ericsson booth a demo of what exactly you just said.
Yeah.
Which is run the OVS and DPDK, then build the Ethernet connectivity to the containers. So that, for us, we program the OVS the same way than for the only issue is that it's not a use case that was discussed before where the container itself is another DPDK, which is problematic today. But as far as I know, there is the new version of DPDK which supports that, including the IO.
Yeah, to add to that as well, I guess just to close the loop, so ideally you want to try to find, if you want to get maximum performance, you want to try to find a way to exclude the kernel from the data path line. And so one way to do that would be to use the VPP shared memory driver that's in development, and like once it's ready to be productized, and you could use that same technique, and not just with VPP. It would certainly be possible to do this with other ones as well, and just so that way when you write out, you're intercepting the write call and then making a decision: is this file descriptor match what one of our managed ones, or is it a normal file descriptor? So of course you get a slight performance impact, but it would probably be negligible at that point.
Just session initiation anyway.
Yeah.
You start passing the packets.
Yeah, and then from there, then when you write, you're literally writing directly into a shared memory that then VPP would then handle, and then VPP would then handle the main VPP instance would then handle the DPDK acceleration, and so that's one potential path that would bypass the kernel and get you that acceleration.
So when we bypass the kernel, how do you deal with RX?
So if you're looking at DPDK, so there's a couple ways that it can be dealt with. So I skipped the eBPF section, but I'll bring it back in because it's relevant here. So I mean, ultimately you're going to have some kernel level involvement somewhere. The DPDK situation, the involvement is, I'm going to give you direct memory access. So what happens is when the NIC card will write into memory, into the process's memory, packets directly. So which means you have to then parse what.
How do you get notified that there is a packet?
Well, that depends on DPDK, like if you poll or so on. It depends on DPDK itself.
I would have to continuously use resources even if there are no packets coming in.
Yes, that's correct. So that's one of the downsides of DPDK.
It's a big downside.
It is, and it's one reason why a lot of people don't like why it's, if you don't need the acceleration at that speed, then it doesn't make sense to bring it in. But if you need that acceleration, like you're doing very high throughput, then it makes a lot of sense. So you have to look at the use case, and that is a problem. Yep.
So the container, the life cycle is pretty short. Sometimes actually less than a minute. But
Yes.
in the scaling deployment, I mean, I'm just thinking how the OVL so quickly push the policy and all the networking related stuff push to the container like a millisecond or seconds. Also the problem.
So yeah,
Especially for big scale deployment.
what you're describing is definitely a problem. So in general, like you look at the spin up time of a VM, you're talking about minutes before you see a production workload. When you're talking about containers, you spin a container, you expect that container to be up on under 100 milliseconds if it's local on the host. In general, I think there's definitely some. I don't want to say that like ODL or some other neutron implementation is going to be slow, but it is something that we need to stress test. It's something that we need to set up a cluster somewhere and say, let's run this thing and see how it acts. So I don't know how it'll act. But it is definitely a major consideration. So
you talked about two networking problems. One was RAM encapsulation. That I
right.
understood. What is ramp up and ramp down problem that you talked about?
Oh, it's not really a problem. It's a technique to move from one SDN to another. So it's used very common, like in layer 3, where you have a node that if you want to move from your layer 3 SDN to your layer 2. Or rather the other way around, from some SDN to your layer 3 like Contiv or Calico. What happens is you forward the packets to a specific system, and then that system knows how to basically NAT into the SDN into that particular overlay. So you basically have these on ramps that you have to have available in order to provide that connectivity with the outside world. It would not surprise me if it was in the works where every host that's on the network could handle it or so on, and then you could have something a bit more dynamic. But in general, that's where the issue arises. So I think there was a question over here.
Yeah, tell me more about how the project Contiv and the other project that you mentioned, and how that factors into some of the issues and some of the questions you've been raising here.
So which issue specifically were you thinking?
Well, just what your perspective is on what Contiv provides, and if it helps solve any government encapsulation issue or the ramp up and ramp down.
Right. So what's interesting with Contiv, it's
and how it interacts with ODL as well.
So Contiv itself has. And both Calico, you can split it down into two major concerns. So one of them is policy. How do we do ingress-egress policy? And the second one is connectivity. And a lot of the policy work has actually been driven by these layer 3, where they've actually focused on those policies. And so when you start, there's a couple changes that have occurred though. So like in the Contiv side, you can actually add in different backends. So it's not just the layer 3 backend. They have a layer 3 backend, but you can plug in other things. What they've started to do with Calico is they said, okay, Calico, we're going to get rid of the. So this, I don't know if this was like 100% official that they were talking on this, but they were saying that instead of running Calico as a data plane, we'll join Calico with Flannel, and Calico will then be the policy engine that handles the ingress-egress policies and ACLs and so on, and then Flannel will then be the underlay that actually runs the data, and so there's a little bit of movement on that side. So when you start looking at that particular area, you should probably take a look at it from like the policy perspective, because in my opinion, the layer 3 solutions, like they do provide a lot of flexibility, but even more important is those policies that they provide.
And does it integrate with ODL?
It doesn't have to integrate directly. So you would install it, and then it should work with ODL. Because it's entirely host driven. You don't have to touch the underlying network itself. But what you end up potentially losing with this approach is like, suppose you decided to go through Kuryr, and Kuryr progresses and into a mature project. Kuryr could bring in firewall as a service. It could bring in load balancer as a service, various other tools. And so one of the more interesting ones is if you looked at Google's like maglev project, which is a distributed load balancer. So you'd be able to bring in some type of similar system that's managed outside of that's not managed by the SDN, by the container SDN, but rather is managed by Neutron, and so you can put your you'd be able to use the underlying network infrastructure, which has a lot more information than the layer 3 API necessarily would have at that time, and leverage some really interesting workflows. So, I mean, a lot of this is speculation, because it's like, where is it really going to go versus where it's at, and so there's a lot of work that needs to be done in this space, and but it's a very fast, very rapid moving space, and so like a lot of the stuff I'm talking about, like if something doesn't exist now, it very likely it'll exist in the near future.
Can you bring the slide that you were doing on the
Sure.
Okay. The second last, yeah, about VNF on the previous. Yeah, this one. What is the VNFM state issue that you mentioned?
So, what I was mentioning in terms of the state is like, you have your VNF manager and it's spinning up and controlling the life cycle of multiple VNFs.
Yeah,
And so the thing on the state is more of an issue as to how you design the application. So many VNFMs should work just fine, where they can rebuild the state, or they store the state somewhere where they can retrieve it. So the issue is whenever you have any state stored somewhere and the container dies, you lose all the state that goes with it. So when you spin it up, it's like spinning up a completely new system. And so you have to be aware of like, does my application have state? If the answer is yes, is it important to preserve it? And if the answer is yes, then the application has to be aware of how to preserve it. You don't want to rely on the container.
The VNF itself has an HA already in place.
Yeah, if it has HA already in place, then you're set. Like you don't.
If not, then your point is that the container is going to do what?
Well, the container doesn't help you in that particular case. With like it'll respin. It could respin the VNFM up, but if you don't have HA already available in terms of the state, then like it's not going to help you on that side. So it's in that case, it's something that you already know. It's like you already have HA on your containers, and what
Yeah, that's okay.
then you're
The
set.
last one, what is the key point here?
So the main key point on that is like if you have a monolithic application, like it won't necessarily cause it to become scalable. So the main point in this is that what your current limitations of your VNF if you have any major limitations with it, that Kubernetes itself will not necessarily solve them. Like it'll support the life cycle, spinning up, spinning down. It'll help.
Are you talking about the generic VNFM or the specific? Or
I'm not talking about a specific one, because like each one is different in terms of like how they handle in
So
terms of how
when
they
you
handle it.
say VNFM, you're referring to what?
So when I'm talking about the VNF manager itself, so most VNFMs should already have high availability and so on. So if it supports high availability already, and it supports being able to scale it out, then you shouldn't have a problem. Like you should be able to just stick it in there, and then it'll handle the life cycle. So if one of your processes dies, then Kubernetes could identify that process has died and then work on setting up another one somewhere else so that your system continues to run. So it helps with the overall life cycle of spinning up and shutting down your processes.
Yeah, hold on. VNFM today, it has to interact with the infrastructure manager.
Right.
Now, VNFM itself has already a built-in HA.
Right.
The VNFs that are managed by a given VNFM, those VNFs, they are looking into the manager for the lifecycle.
Right.
Now, what is the notion of Kubernetes is going to not magically make a VNF scalable?
So what I'm specifically referring to is that if you have multiple like VNFMs, like suppose you're running a really large deployment and you want to do some type of segmentation between them, then if your VNFM was designed to be able to be horizontally scale, then you're in good shape. But if your VNFM was designed, like suppose it's a very simple one, like you're running some reference architecture or something similar, it won't provide what the application itself should do for itself. So that's the primary idea behind it. So if you're running a VFNM that's already robust, it has the ability to.
This is only the management entity. You also
Correct.
have an application control.
Right, so you can think of it as like a VNFM, like it's able to work out like, hey, is this thing followed? So you can you basically standardizing those particular tools because you already, if you're running like in terms of Kubernetes, if you're running applications with Kubernetes and simultaneously you're running your VNFM, it's possible to use that same infrastructure, so you don't have multiple infrastructure that ends up copying the exact same problem. So it's a path that some groups are looking at, but it's something that's very early on. So basically, the system that would manage your VFNM, like that particular, like Kubernetes does have the ability to help manage that lifecycle and seed it.
So is this already an issue for ODL or this is
It's not an issue with ODL at this particular.
because ODL is the control.
Right.
This is more like lifecycle management.
Right.
Then you, on top of this, you have an application control.
So one example with ODL, like if you wanted to stick the ODL controller itself, like you could stick it into a container because it's just a Java application. And what you could do is, so there was some work that was being done in the past 6 months or so, and probably spanning back a bit further, in order to add high availability into ODL. And so that particular, so ODL itself has to be highly available. Like Kubernetes itself won't provide that for you. But what you could do is you could run Kubernetes like bare metal, and then you could run OpenStack infrastructure, or you could run OpenDaylight itself within pods in Kubernetes, and let Kubernetes manage. So suppose Neutron fails on you for some reason, or the system literally dies on you and you have to get it replaced. You're not stuck there with nothing, like having to get someone to revamp it up somewhere else. Like Kubernetes will then detect that it's failed, and then identify another system with resources and then spin it up. And so, and ODL in high availability mode, assuming that it doesn't run into any problems with how it manages state or so on, would then just like you'd have a pause in terms of maybe you wouldn't be able to spin up a container or a VM, or maybe if you shut down, you have to wait until it properly recovers those resources. But then at that point, you know that you're going to get another instance somewhere, and then it'll continue working on. So you end up with it's a component in the self-healing process. So that's the general idea.
All right.
So. Anyways, I think we've come up to the end of this. Does anyone else have any questions before we finish up? Very well. Thank you very much. The differences. It turns out there's a lot of interesting differences between them that are quite subtle. So when we talk about a container, it's not moving. Let me try resetting it. Oh, weird. Okay, worst case scenario, I'll pull it out and put it in again. So, let's see if I take it off full screen. Okay, I think I know what I'm gonna do. I'm gonna move this here. And, see. See if I hit present, does it do the same thing? Okay, so the only problem is I can't see it. Give me a quick moment and I'll fix this up real quick. Is it okay if I use one of the microphones instead? Okay, my apologies, which is the most common one, and the second one is using the ton tap, which the difference between the both of them is the veth pairs are the data path in order to manage and to work with them is non-blocking, while IOCDL has some performance issues. So in general, if you have a choice, if you're want to jump into some of this, I highly recommend you look at veth pairs rather than looking at the ton tap. And so typically what ends up happening, like early Docker, if you looked at the networking structure of it, the early structure was you set up a Linux bridge and you then hook up veth pairs. One side of the pair would go to the bridge, the other side of the pair would go to the container inside of the new network namespace. So real simple. And so what we're in more advanced use cases. So if you look at the code in Flannel as an example, one pair goes to the container, and then the other pair exists on the within the host. But what ends up happening, I don't know if it's a host or if there's another container that it brings up with that inside. But what ends up happening is that second veth pair is then read using standard socket I/O. You can do read, you can write to it, and so it'll read the data off of that, and it will transform that into UDP or into VXLAN or wherever it needs to go. And in general, a large number of SDNs work in that exact same way. So OVS is a little bit more interesting in that they have their own style of bridge. So they have a patch, but in general, yeah, with OVS, what you want to do with OVS is there's a set of commands you can run that'll create an interface, and that interface will then back into the OVS bridge, and it's sort of like an advanced CH route. And so the CH route ends up, the process is then routed to that particular CH route, and in ideal circumstances, you can't escape. There are exceptions to that, like if you run it in a privileged mode, or if someone were to find a bug in the kernel and exploit it, then yes, they could potentially escape. But in general, processes are isolated to that subdirectory on the host. So each one gets their own network namespace, which is really important for us because that allows us to do really interesting workflows beyond what the host provides. So it means it gets its own IP address, gets its own DNS. When you open up a file descriptor, that file descriptor is bound to that particular namespace. Whenever you run IP tables, turns out even IP tables is also namespaced. So if you have enough privileges, and usually you don't, but if you have enough privileges, you can actually run IP tables that's bound to that namespace. And so a really good talk, if you want to see into the details, a lot of this is Jaume Devesa created Anatomy of a Container Namespace, C groups, and some file system magics. And he gave a really great talk on this. I recommend you look it up if you want to get into like the really nitty-gritty details. So what's interesting with a network namespace is you literally get a full network stack. So you get your own network interfaces. It traverses over its own. You can hook them up to bridges properly, create novel workflows. And so usually there's two, in most SDNs you see two forms of connectors. So the first one is veth pairs. Okay, well in that case, let's go ahead and get started. So I'm Frederick Kautz. So unfortunately my counterpart Ivan was not able to make it today, so it's just going to be me. But he did help me put together this deck, and we spent quite a bit of time trying to work out what it is that we want to show all of you. So in general, what I'm going to try to do is I'm going to try to describe move it a bit forward. So I'm going to try to set like what is a container. So I don't want to make any assumptions that people have a full understanding of what a container is. And what I want to do is talk about a container from a networking perspective. What's out there, what's available, what can you potentially use now, what's coming through the pipeworks. I want to describe as to like why does everything not just work now? Like we have all this stuff with virtual machines, and why can't we just go off and reuse a lot of that work? Why are we as a community re-engineering a lot of the tooling and APIs that exist? And we'll also cover some of the deployment models that we've seen as well, and we'll cover some of the technologies. So in terms of like what is a container, or what is it that we're going to try to focus on? So first, what is containers? We're going to focus on container technology, container management and orchestration, and container networking. So moving in, so exactly what is a container? So a lot of people like to think of containers as sort of like a virtual machine. Like you stick this process into this box, this container, and then it runs, and you can start it like a VM, you can stop it like a VM, and conceptually it helps a lot to get in. But when you start looking at so anyways, going back to where we are, let me go ahead and hit present. Okay, so when we talk about what a container is, so a container in a broad sense covers both containers as what we commonly hear. It also covers VMs, covers even a process itself can be considered a container. But when we talk about containers, we typically talk about specifically process containers. So think of a process container as an environment that has been set up by the operating system in order to isolate a process. So it gets its own file system, it gets its own network stack, it's its own process file tree, and so the kernel does extra bookkeeping in order to make sure that it all works. So this is very different from a VM, where a VM will literally emulate an entire system and hardware and NIC cards and so on. So okay. So how does this end up working? So there's a few technologies. This is not exclusive. This is not like totally inclusive, but in general, the early most important parts are C groups, which allow you to monitor your resources, allow you to limit your resources. A lot of this work around C groups, if my memory is correct, was contributed by Google, and Google used them internally for several years, and the rest of the community, like C groups was available, but it didn't really catch on because of some of the difficulty. The next one is mounted file system. So what ends up happening is every time you run a container, literally a new mount will be created in a file system tree,